Yes, I guess so.
Because she made me promise I was going to do it.
Yeah, fine.
Okay, welcome back. So lecture 2. This is Lie theory. One example. Topic of this lecture. Well, let's recall where we were. So recall a Lie group a Lie group G is a group that is also a manifold such that the group operations are smooth. That's inverse and multiplication and assigning an identity. And for us, most of the information about a Lie group is contained in a Lie algebra. This is defined on the vector space, which is the tangent space to the identity of the Lie group. And let me fix something that I didn't do last time, which is to give you the definition of a Lie algebra. G is a vector space. And for us, this always means over the reals or complexes, although you can work more generally, and Lie theorists certainly do. With an operation. Like this. With a bracket. Taking two elements of the Lie algebra and giving an element of the Lie algebra. So it's called the Lie bracket. Satisfying the following axioms. The bracket is bilinear. Linear in each slot. It's skewed symmetric. Bracket of x and y is equal to negative bracket of y of x. And it satisfies this identity called the Jacobian. Bracket of x and y with t, the cyclic permutations of x, y, and z. Equals to 0. us, all our examples of Lie groups will be matrix Lie groups, meaning they are subgroups of GLNK for some N and K means R or C. And when you have a matrix Lie group, then you get a matrix Lie algebra. So the Lie algebra of this Lie group is going to be a sub-Lie algebra of GLNK of n by n matrices with entries in K for some n. This is just the set of all n by n matrices. Okay, with bracket. Given by the commutator. So it's a good exercise to show that GL and K is a Lie algebra. Which means to show that this commutator bracket satisfies the Jacobian.
But this Q symmetry is obvious because it should satisfy Q symmetry too, right?
Yeah.
Yeah.
So where were we? So last time, and now this time, goal to understand the representations SU2. 2 by 2 matrices with determinant 1. Two by 2 matrices with determinant 1, such that the conjugate transpose is the And last time we discussed
Maybe we should say C2 are the 2 by 2 matrices because.
right, I said that here for K and
Yeah.
N, but it does not have to say it here. 2 by 2.
Yeah, because it's non-standard.
Absolutely, it's not saying. This is my notation for matrices. Okay, so last time we discussed the following equivalence, that reps of the Lie group SU2 are in one-to-one correspondence with representations of the Lie algebra of SU2. Of all 2x2 matrices, such that conjugate transpose is negative and trace is 0. But we also discussed how reps of the Lie algebra SU2 are in one-to-one correspondence, complex reps are in one-to-one correspondence with reps of the Lie algebra SL2C. This is the complexification of SU2. It's also the Lie algebra of all 2x2 complex matrices with trace 0. Are there any questions about this? This is our starting point for today, basically.
So just
Please.
so X is just algebraic the group, right?
X is a matrix.
Okay.
It's a 2x2 matrix.
Okay.
With entries of the complex.
Not in the group, in the vector space of the Lie algebra.
Okay, so it's slightly the
The Lie algebra, yes.
Yes.
Thank you.
Yeah, it's a little confusing because both the Lie group and the Lie algebra consist of 2x2 matrices.
Yeah.
But this is a vector space. This condition is linear. These conditions are linear. This is not a vector space because these conditions are not.
Okay, so there's a one-to-one correspondence between group and the algebra.
The
Right?
representation.
The representation of the Lie algebra and the group of S2, right?
That's right. That's right. So this is where we were last time. We went a little bit further, but we also noted, and I did this quickly, so I'm going to do it a little more slowly, that it suffices when studying the representations of any of these, just studying the representations of all of them because they're the same. Suffices to consider irreducible representations. So, or irreps, for sure. So a representation, representation V, some vector space on which the group or the Lie algebra acts by linear transformation, is irreducible. Yeah. Or any sub-representation is a W in B such that, which is a W in B, then either W is 0, the 0 vector space, or W is all of B, the whole vector space. And here, by subrep, what I mean is that W subspace and GW is in W are all W and G in SU. So you can act on the subspace with all your group elements, you stay in that subspace. Another way that people say it is they say that W is invariant under the group. So why does this suffice? Why does it suffice to think about earrings? And it's because of the following theorem. Representations finite dimensional. We're always assuming our reps are finite dimensional here. Finite dimensional representations B SC2 are completely reducible. Which means that B is the direct sum of some finite list of irreps. WI So this is a very important theorem. We don't quite have the technology to prove it, but the proof works the same for any Lie group like SU2, which is a compact Lie group. So even though I'm going to introduce a tool that in this proof that we haven't talked about before, it's a very common tool. It's a very important idea. So proof. But W E be be a sub. The results follows by induction on dimension of B if we can find a complement to the vector. That is a subrep U in B, another subrep, such that W plus U is all of B. So now we're going to do that. We're going to find this complement. So to do this, B with a SU2 invariant Hermitian So this is a map B cross B to C such that it's linear Does anyone know what a Hermitian product is? Is this okay?
Yeah,
Should I
the
say
linear,
it?
I think is positive definite, right?
Yes.
Yeah,
yes.
that's the only dot, I think.
Okay.
Inner is positive.
But tell that to be speaking. Tell me.
Real no.
Okay. Okay, so this is an inner product on a complex vector space. It's linear in one variable, but anti-linear, that is conjugate linear in the other variable. And it has the property that EV, this is real, this has to be real. Greater than 0, and it's equal to 0 if and only positive definiteness. So how do we find? So we say this is invariant if acting by the group elements on any pair of vectors is equal to the inner product. Leaves the inner product unchanged. It's for all G, yes, 2, and all vectors E and W. So we're gonna use a big fact. S2 has an invariant measure called R. This is true of any compact Lie group. To find our invariant in the product, pick any Hermitian inner product bracket prime, just any Hermitian inner product. It's a vector space. If I'm in a vector space, I can pick a basis, pick an inner product by saying how those basis elements pair. And average over the group. The product of V and W is equal to the integral over x2, the inner product of GV, GW with my arbitrary inner product, G. And because this measure is invariant, one can show that this inner product is invariant. So once this is done, now choose U, our complement, to be the orthogonal complement of W. And that completes the proof. So we did a really fancy thing. We used this invariant measure, but in the end, we got a complement. And that's all we need. Any questions?
Yes, I have
Yes.
a question.
Please.
So, on the right blackboard, you erase just this U plus V, U plus W isomorphic to V, right?
Yes.
And this is not meant as isomorphic as vector spaces, but as reds, right?
That's right.
Okay, and so here you just gave us the vector space, but maybe I'm supposed to see that the vector spaces are really isomorphic as the reds. Or maybe I just don't see it. Because you just say T is such vector space, and then this gives us the isomorphism of representation.
So yes, choose this subspace. And then because this inner product is invariant, this is going to be a subgraph as well as a subspace.
Subspace as C, but sub representation.
Right, so let me
Yeah, this one.
Yeah,
So, what will be? You show that it is close. Take an element of the orthogonal or the branching system of orthogonal. Why? Because of its size.
so
Yeah.
U is defined to be the perpendicular to W. And that's the set of all V in V such that using this inner product, V W is equal to 0 for all W. Right? So the question is, if I have a V here and I act on it with G, is it still in W curve? So GV, inner product with W, well, it's invariant. So this is V G inverse W. Right? I can act on this all with G inverse. And that just moves this G over here. But then this is a sub, this is a W itself is a subgraph. So this is still in W. So this is equal. Sure. Please. Yes.
So are we supposing that W is irreducible? Or
No, we're not supposing that W is zero. We're just supposing it's a subgraph.
Okay.
The idea is that, so the induction works like this.
Yeah, okay, so we iterate that until we like we have an initial guess and then we go and we have sorry, we have
Let me just spell it out just a little bit more. So if the so if V is irreducible, then no. Okay. If not, then there's W in V, a subgraph, and it's proper. It's not zero, it's not V. It lies in between. Such that dimension W is strictly less than dimension. Find the complement. U, a subgraph, such that W plus U is all of V. And then, because W is in between V and 0, U is also. So, dimension of U is also strictly less than dimension of V. And the induction at last implies W and V, W and U are completely reduced. In the edge. W and U are completely reducible, so each one of those breaks up into a sum of irreps. But that means that V, which is the sum of them, is the sum of irreps. Okay? Other questions?
If the canonical is
Is there a what?
canonical
On SU2. So SU2 is not a vector space, but the Lie algebra, in fact, does have a canonical inner product. It's called the killing form. I'm not sure how much I'm going to talk about it, but yes, there is. Okay, so. So we're going to assume from now on, the rest of this lecture, well, maybe not the rest of this lecture, but at least what we're talking about SU2. Assume the irreducible representation of SU2. Then by our correspondence, it's also an irrep of the Lie algebra. And of the complexification. So we're going to try to understand irreps of SL2C. So understand SL2C by acting on them with our favorite basis. It looks like this. Upper triangular matrix. Lower triangular matrix. Diagonal. These are not matrices in little SU2. These are not in this Lie algebra. This is the real reason that I wanted to work in SL2C, because this basis, as we'll see, works really good. And please note that this basis satisfies that acting by H, sorry, bracketing with H on E is 2E. Bracketing H with F, negative 2F. And bracketing E with F. And since there are only 3 elements, and the bracket is skew symmetric, these are the only interesting brackets.
That's one more question, please. Before you said that SL is complex tensor of SU. What do you mean by that? That's like the representation you take in complex. Is it the
Yes.
last row in the first and the second row was a linear representation? Or is it the group is already complex, like the matrices are?
The matrices are complex, but this is not a complex vector space.
Okay, so you're acting on a real vector space, and that
This
was
is a real vector space, it's a complex vector space.
okay.
And it just so happens that if you take this vector space and tensor it with C, in other words, complexify it,
So,
you get this vector
yeah,
space.
and you have an introduction.
Yes.
Thank you.
That's a good exercise, and it's an exercise that I assigned in the last lecture, was to show that if you tensor this with C, also you get a bracket operation. If you take any Lie algebra and tensor it with C, then your bracket also becomes, you get a linear bracket, C by K.
Okay.
And you get this. Okay, so we're going to understand this representation theory using another big fact that I went through, which I also mentioned last time. That H, this diagonal matrix, is diagonalizable in any representation. So what does that mean? So that means that for any representation V, I can write it as a direct sum of eigenspaces. So these V lambda are eigenspaces. For the action of it's a complex number. This is another reason to work with the complexification and to work over the complex numbers, because if you have a diagonalizable matrix, it's diagonalizable over C. Okay. So what this means, let's just translate this into symbols. This means that H acting on V is lambda times V for any V in this eigenspace. So we're 1/3 of the way to understanding this representation. We understand how one basis vector in our algebra acts. We can understand the other basis vectors, maybe we can understand this representation. And remember that this V is an array. I'm assuming from now on that V is an array. So what we'd like to know is for V lambda, what is E so the way we decompose our representation, we've decomposed it into eigenspaces of H. So what we should know is how H acts on this. That's what we want to know. So check how H acts on E acting on V. So acting on. This is a fundamental calculation. The way that you do this is using the commutator. I can change this order, but at the cost of introducing, that's a mistake. At the cost of introducing commutator. We know what H acting on P is. It's lambda times. We know what H commutator E is. It's 2E. And this lambda is just a scalar. It just comes out. This is a linear operator. So in the end, we get lambda is 2. So that means D is in the lambda eigenspace, and EV is in the lambda plus 2 eigenspace. And a similar calculation shows that FV is in the lambda minus 2 eigenspace. So here's our picture so far. We picked an eigenspace. E takes our eigenvalue up by 1. F takes it down, sorry, up by 2. F takes it down by 2. And H just keeps us where we are. Any questions? It's just for one eigenspace in our representation. So because V is finite dimensional, then eventually this process of going up has to end. There has to be some point where you keep hitting your vector with E and it dies. It has to be 0 at some point. Must terminates. So let's call that spot where it terminates J. J is the biggest eigenvalue in this sequence. Ej be the last non-zero, the last eigenspace. Eigenspace is non-zero by definition. So far, J is just another eigenvalue. It's just another complex number. But we're going to see in a few minutes that it's a instrument. In fact, it's a positive. Not negative. For any vector v in Vj, we must have EV equal to 0. Because if EV were non-zero, then it would be in J plus 2. And that's too big. J is the last one in this sequence. Such a vector V in Vj, which satisfying EV 0, it's called highest weight. With weight J. Now we've hit the end of where E can act. E can't go any further here. But we can go backwards with F. We consider V, FV, F square V, etc. And again, because it's finite dimensional, this has to end. There has to be some place where this sequence becomes 0. So F n plus 1 of v is 0, where Fm of v is the last one where this is constant. And now n is clearly a non-negative, a natural. So proposition D FV of log Fm V is the basis for V. All right, I'm going to prove this, and then we'll take a little break. Good. Let W be the span of these vectors. And W is a non-zero subspace because V is non-zero. And it's a subring. Because if I act by F, I just go along in this sequence. If I act by E, I just go up in this sequence. If I act by H, I just stay where I am. So, because it's an irreducible representation, V is irreducible. W is equal to V. And because, so that proves that it spans, but they're also eigenvectors for distinct eigenvalues, so they're linearly independent. So it's a basis. Any questions? Okay, let's take a 5-minute break. Should we take a 5 minute?
Sure. So maybe you have questions?
Yes.
We have proven yet that J is a positive integer, right?
Right,
We're
that's
gonna do it next.
next, yeah.
Yeah. So let's stop the recording and let me try to upload it to YouTube if I can.
Okay.
Because at some point we will have to do it.